Hello everyone, my name is Hesamaddin Emamipur and today I will talk about frequency stability improvement in power systems using an internal model control based PID controller tuned by genetic algorithm. In this presentation, I will explain why frequency stability is important in power systems and how we can improve it using a smart type of controller. This controller is based on IMC and uses a genetic algorithm to make it work better. I hope you enjoy the presentation and find it useful. Here is what I will talk about in this presentation. First, I will explain load frequency control and then the PID controller. After that, I will introduce the IMC method and how it works with LFC. Then I will talk about using the static synchronous series compensator or SSSC in load frequency control and explain how the PID controller is tuned using a genetic algorithm. Finally, I will show the simulation results. This slide is about automatic generation control or AGC. AGC is a control system that automatically adjusts the power output of multiple generators to keep the system balanced. Its main goals are: 1. To keep the system frequency at the correct level. 2. The control to the power exchange between different areas. Third, to make sure the power system is generated efficiently and economically. AGC help make the power system more stable, reliable, and automatic. We have two important control issues in power system. First, active power. Control of active power is closely related to frequency control, and frequency is inversely related to continuous load variation. Second, reactive power is related to voltage control. Load frequency controls the power output of turbines. It keeps frequency and power flow stable. LFC is an important part of automatic generation control AGC. LFC helps keep the system frequency stable. Its main goals are remove line term frequency error. Second, reduce unwanted power flow between different areas. Third, follow changes in the load quickly and accurately. Finally, keep frequency response smooth and with low overshoot and fast settling. When when power of generation less than power of load, the frequency drops rapidly. Second, in the absence of appropriate system response, it causes the frequency to deviate from the operational range of the equipment. Finally, power system collapse. In this slide, you can see the main control loops of the generators. Upper loop is the loop of voltage control, and the bottom loop is the main loop for load frequency control. In an isolated power system, there is no tie line with other areas, so the main goal of frequency control is to keep the system frequency at its nominal value 50 or 60 Hz. After a disturbance such as a sudden change in load, the control system adjusted the generator output to restore balance between generation and demand. This model helps us study the basic dynamic behavior of frequency in response to change, load changes. Uh, Also, you can see the transfer function of governor, turbine, load generator, speed regulation, and controller. In this slide, we show how frequency control works in interconnected power systems. In isolated systems, frequency control only focuses on bringing frequency back to normal. But in interconnected system, we must also control tie-line power between areas. So each control area must manage both its local frequency and power exchange with others. PID controllers. One single input, single output process, like Ziegler-Nichols method, classic tuning method based on system ultimate gain and period or gain phase margin method ensures stability and desired margins by analyzing the open loop frequency response. Second, optimization based tuning. Assume a PID structure and tune parameters using optimization technique like minimizing error or performance index. Third, model based design reduction. Design an advanced controller like LQR or H infinity and approximate it with an equivalent PID controller for simplicity. Uh, this ways show all way for PID controllers. In this slide, we explain internal model control or IMC. IMC is one of the key techniques for controller design. It works based on having an accurate model of the system, allowing the controller to provide a stable and prices respond to both input changes and disturbance. We explain the composition of the system model into parts. This system model uh, p-tidal equal pm times pa. Uh, PM, the minimum phase invertible part of the system, representing the stable and controllable dynamics, and PR, the non-minimum phase part with unit magnitude capturing non-invertible elements such as unstable zero or time delays. Finally, the equivalent controller is given by K. As a result, approximation of controller code to a PID controller KP, KI, and KD. Sorry, excuse me. In this slide, we explain how power electronic devices like the static synchronous series um, compensator or SSSC help control frequency. The SSSC reacts very fast to sudden load changes and reduce the peak frequency deviation. After that, the governor slowly brings the frequency back to normal over time, so their actions happen at different time stages and do not overlap. In this slide, we can explain about the fitness function. My fitness function is to minimize overshoot or undershoot and settling time. Our goal is to tune the parameters lambda and lambda d in internal model control structure using a genetic algorithm in order to minimize the fitness function. As I mentioned before, the minimize function is the minimize overshoot and undershoot plus settling time. This slide shows the step-by-step process of how the genetic algorithm is used to optimize controller parameters. First, we initialize a population of possible solutions. Then we evaluate each solution using a fitness function which measures how well it performs. Third, the best solution are selected and through crossover and mutation, new solutions are generated. Finally, this process repeats for several generations until we reach the best optimized parameters. In this slide, we show the schematic of a power system used for simulation. It includes four areas. Area 1, 2, and 3 have similar thermal units, which reheated turbines. Area 4 is a hydropower plant. The performance of the proposed PID controller designed using a genetic algorithm or GA within the internal model control framework is evaluated under three different scenarios to assess its effectiveness and robustness. In scenario 1, the proposed controller is compared with the IMC-based PID controller not optimized under nominal system conditions, where the solid line represented the response with the proposed optimized PID controller and the dotted line correspond the PID controller not optimized. Simulation results demonstrate that the proposed controller achieves better performance across all metrics. In particular, it significantly reduced the settling time and overshoot while minimizing steady-state error and improving overall system robustness. You can see the frequency deviation in area 1, area 2, area 3, and area 4. In scenario 2, the PID controllers tuned using the genetic algorithm are tested under a 50% reduction of the key system parameters in the first three control areas. This parameters variation aims to demonstrate the robustness of the purpose controller against power system uncertainties. Frequency deviation response across all four areas are shown in figures where the solid line represented the response with the proposed optimized PID controller, and the dotted line corresponds the PID controller not optimized under nominal system conditions. Simulation results confirm that the proposed controller maintains strong robustness against the system parameters change. Also, you can see the frequency deviation in area 1, area 2, and area 3 and area 4. In scenario 3, implementation of the proposed controller in presence of presence of SSSC, the proposed PID controller is implemented in the system aligned with the static synchronous series compensator or SSSC. The objective is to evaluate the controller's capability to maintain frequency stability under dynamic conditions and external disturbance. The SSC plays a crucial role in enhancing the system's dynamic response. By injecting a series voltage, it improves the frequency profile and effectively reduces oscillations. Simulation results indicate that the proposed PID controller, when used in conjunction with the SSSC, has a strong performance in damping frequency deviation and maintaining system frequency within acceptable limits. Also, you can see decrease under shoot. This study introduces a high-performance internal model control-based PID controller optimized using a genetic algorithm to significantly improve frequency stability in power systems. The controller demonstrates exceptional dynamic response with simulations confirming faster settling times, minimal overshoot, and net zero steady state error compared to conventional methods. Thank you for uh, watching my presentation.